Hello and welcome all the audience from Israel and out of the country, and thank you for joining us this afternoon to our bio and medical optics session. Last year, and even more than a year, we faced new challenges that took science to the edge. All people understood how it's important to lead and understand what is technology, how to take ideas and to implement them as fast as possible. And at least in Israel and in the rest of the world, we are start seeing the end of the pandemic and the very serious situations that we had. Still, we are online in this amazing platform. We hesitate a lot whether to run this conference and what is the best way to do that. And here we are almost at the end of the second day with huge success. I would like to thank Shlomo and Nofar and the companies that are operating this amazing platform. And I'm sure that in the next 5 lectures, 1.5 hours, we will enjoy and learn a lot. Mainly what's happened during the last year make us much more clearer that medical biology and combination with other technology, as we are in the optics segment, can survive, can lead to better future and to get out from crisis. Although we are not dealing with vaccinations or dealing with treatment, in the optics segment, we did a lot to improve the quality, the identification of the disease. We managed to invent many patents and technologies that help the medical doctor to identify the situation and sometimes to detect the disease before infecting others. Beside to the pandemic, I would like to focus on 2 main things that happened recently. One is the bioconvergence combination of life science and medical with engineering. Clearly not only optics in the engineering, we are talking about big data and analysis, but the combination of optics and engineering with life science had a new title of bioconvergence. And in these days, you can find in each country new challenges and new places that can implement this kind of collaboration and implementations that took us to the next generation technologies. The second main thing that's happening is combining more and more modalities of imaging in life science. Well-known PET-CT that combining 2 different technology of structure imaging and molecular imaging. And in these days, there is a wave dealing with CMI, correlative multimodal imaging, that I can tell you about big efforts that we are doing in Europe. Part of the speakers and the Professor Jorgen Popp are part of this efforts of taking different labs that dealing with different modalities, combining them together and providing new vision and new way to see disease, to find drugs, and taking all our challenges to the next step. Today we have 5 talks, 3 out of Israel and 2 Israelis. In addition to be great scientists, they are friends, good friends. We will have from Germany, Russia, again Germany, and 2 guys from Israel that are not coming from universities, both of them from college or something that's similar to university, from the Vulcani College. And all together we will have a very nice picture of what is going on today in the segment of optics and diagnostic and healthcare. So let me introduce our first speaker, Professor Jorgen Popp. Professor Jorgen Popp, leader of many segments, but main title is coming from the Leibniz Institute of Photonics and Technology. Today, Professor Jorgen Popp will talk about biomedical photonics, key to better personalized health care. Professor Popp.
Yeah, ladies and gentlemen, many thanks for this kind invitation to speak about biomedical photonics key to better personalized health care? Well, I'd like to start with this picture, which is quite common. You're sitting in front of your physician, you're feeling not good, maybe you have a cough or an infection, and after a certain time you're leaving with a certain prescription. For example, you will have an antibiotic treatment. Well, the question is, how does it, the physician knows that this would be the appropriate treatment without doing any, let's say, measurements, objective measurements. And therefore, we'd like to provide a precise diagnosis before then the physician can start with a target therapy. And I'd like to start with one mega trend, which is related to the mobile society. And this is related with infection diseases. Like the corona pandemic is showing that we are quite, let's say, infection can be very harmful to our society, to our entire social life. And the question is now, what is needed for an optimal and personalized treatment? And certainly when we talk about infection diseases, first of all, you need to have some information about the host response. What does it mean, host response? Is this what you are, let's say, you are feeling, what your body is showing as symptoms? Is this related to an infection or something else? Or just the normal inflammation? Then if it's an infection, then certainly we need to know something about the pathogen, the antimicrobial resistance as well. So the first part of my talk will be about this topic, and I'd like to start with the host response. And there we have to look at the role of the immune cells, and because the immune cells, they are interacting with the microbes, and this could be the neutrophils, the monocytes, the eosinophils, and when they are interacting with microbes like fungi, yeasts, or virus particles, bacteria, then the cells are showing some cellular response. And I'm not going into the details, but this can be shown on the molecular level. And therefore, we'd like to use Raman spectroscopy in order to get this molecular information from these immune cells. Why Raman? Because it's, I would say, the most simple technique. You just need a laser. You're shining with a laser on your cell, for example, of a bacterial. Then you get all this chemical information. You get something like what we call a molecular fingerprint. And well, when you're dealing with biological samples, then this is quite challenging to interpret this Raman data. Therefore, you need somehow machine learning, deep learning, artificial intelligence in order to interpret this complex Raman data. Well, this is when we started in 2003 in Jena. We started with big equipment. Then this was already our first, let's say, portable device called OMIP. And then in 2010, together with the company RepID, now MeBig, we introduced the first bioparticle explorer into the clinic. And then later on, together with the group of Ivan Shi at the Leibniz Institute of Photonic Technology, we were able to have a home-built Raman spectrometer for high content, but also high throughput Raman measurements, which allows us to measure many, many cells in a very short period of time. I'm not going into the details. So what we have been doing is, for example, in order to measure the immune cells, so we were taking the white blood cells, we isolated them from full blood, then we do the Raman measurements, and then you get some spectral features like here from the white blood cells, from the neutrophils of the T lymphocytes, and then you can, for example, go for, let's say, you're looking at the DNA versus the cytoplasm, and then you get here detailed information. Where are the lymphocytes? These are the monocytes, neutrophils, just by looking at the size of the cells as well as the distribution of the nuclei. The question was then, how many cells do we need to measure? Is it sufficient to measure 1, 5, 10, 100? What we figured out is, in order to have really a reliable distribution of the various neutrophils, eosinophils, basophils, and so on, let's say the distribution of the white blood cells, which is really representative to the health care status of the patient, you need to measure something like 1,000 or 1,500 cells. If you measure just 100 cells, this is not really sufficient to be representative to the patient. And these were our first results when we compared healthy donors and patients. And here you can see in white the Raman readout, the clinical readout, and you can see this is a nice agreement just looking at the Raman data with this high throughput, high content Raman screening. And you can see that we measured something like 24,000 cells. This was one of our first approaches here. The acquisition time was something like 0.5 seconds. Now we can reduce the acquisition time even further, and this allows us to measure many, many cells. And here you can see all the cells which have been measured. Well, in order to learn more about the host response, we were doing some spiking experiments. So we used neutrophils isolated from patients, and we spiked them then with various pathogens. And then we did our Raman measurements, and then the analysis here, for example, we have a principal component analysis together with an LDA, linear discriminant analysis. And we look, for example, at the infected neutrophils to the control, which were not infected, and then this of the bacteria, but also then we did, for example, the same with the fungal infection control versus the infected one. And to summarize this spiking experiments, what we can see is if you look for the neutrophils which have been infected and non-infected, then we can differentiate them with an accuracy about 90%. If we now go for the infected one and we look at the fungal infected and the bacterial infection, then we can separate them by 92%, and even we can go further. We can even, just by looking at the neutrophils, the Raman data, we can easily identify, for example, this cell has experienced a gram-positive versus a gram-negative with an accuracy of 84%. Well, now you will say this is spiking. This is not really something which is really bringing us further. But the point is, we get also some samples from the intensive care unit, direct patient sample, or from the intensive care unit from the emergency department. And there we were looking at the cells with our high throughput, high content Raman approach. And here the red could be identified as virus infection, and the black one is a bacterial infection. And this means here, in this case, you need an antibiotic treatment. In the other, you need an antiviral treatment. Unfortunately, we didn't have any samples coming from a fungal infection. Well, this means that spectroscopic information can lead already to a diagnostic-driven therapy, meaning that you can really go a step further just by having this spectroscopic information. Then we were looking at some sepsis patients. This was in a European project. These results achieved, as well as the device I was talking about. Hemospec is the approach. And we had patients which have a viral infection with organ dysfunction, as well as people with sepsis. According to the sepsis 3 definition. Again, the workflow was the same as I mentioned at the very beginning. And then we can look at the receiver operator characteristic curve, where we looked at the infection, and we can nicely see that Raman, as well as the biomarkers, these are just some protein measured in specialized lab, have the same area under the curve. The balance accuracy is a little bit less, but if you combine them, then we have something like 90% balance accuracy, as well as area under the curve at 90%. If we go now for people having a sepsis, for sepsis detection, and we just look at Raman and combine then Raman with biomarkers, or this qSOFA score, which is this is the definition, sepsis definition 3. With the biomarkers, you can see that Raman with the biomarkers is already as good as 92%. And if you look at the qSOFA and compare this just with Raman, then they are quite similar. Yeah, and if you combine both, then you can see that we have really something which is really unique and gives some further information within patient having a sepsis. This approach we have then also used for patient having a COVID infection. So we have here been part of the ICROS-CORA clinical study, where we had patient from the ICU with sepsis, having a sepsis according to the sepsis 3 definition, or SARS-CoV infection. And we have measured them as a function of time. And here you can see the different time days. And when we go a step further and we look at the different time points, you can see here how many samples and patients have been measured. And just to summarize this, what we can nicely see is just by using, again, the white blood cells, We can look at people having sepsis and a SARS-CoV-2 infection versus another infection with a nice sensitivity, and the balance accuracy is around 78%. And this gives us already good hints that this approach is very powerful, but it needs to be evaluated further. And here you can also see the ROC curve, and you can see we have an advanced, the area under the curve is 86%. And this already shows, as I said, how powerful this approach is. Well, if we then want to go for the antimicrobial resistance, then the question is, what is, first of all, the antimicrobial resistance? What is the dilemma? And here you can see just a map of Escherichia coli being resistant against the third generation of cephalosporins. And you can see in 2002, everything was more or less okay. If you look at the time running, then you can see more and more resistance is coming up. And this means that this type of antibiotic treatment is not anymore sufficient. And if we continue this way, then at the very end, there will be no functioning antibiotic drug anymore. This means we are on the border of a post-antibiotic era where we have no functioning antibiotics anymore available. This means in order to avoid this, we need to be very precise. We need to identify the pathogen as well as the antibiotic resistance in order to do so. So what is the current situation, the state of the art? It's based on cultivation, and then there is some specialized measurements. At the very end, it takes quite long, so there is a need for a fast and precise method. And we have developed, based on Raman spectroscopy, a technique which gives us all the information in a very short period of time. And here you can see our approach. This is the so-called Raman bioassay. We have here developed a specific chip where we put different antibiotics with different concentrations on this chip. We have some electronic structures which allows us to push the bacteria into the center of this chip device. Then we do Raman measurements, but also we do microscopy in order to see how is the change of the morphology. And this allows us really to go for a quantitative access of the antibiotic resistance. And here you can see some Raman data, and you can see there is a change. For example, if you change the concentration here, especially in this range where we have the DNA versus the CC stretching vibration, and we are working also on a complete automation of this device, as you can see, so that we can measure in a very short period of time many of those chips. And what you can see here is that we can get a complete antibiogram having different antibiotics, and then we can look at the Raman data, we can look at the microscopic images, and then we can see there's an inhibition, there's a growth, inhibition, there's a growth, and we can even go for a quantitative assessment, and this allows us really to do this complete in a very short period of time. And if you compare this with other techniques, then our advantage is that we are doing this in something like less than 2 hours from getting the samples to the results. Yeah, within the last 6 minutes, I'd like to go for another topic related to cancer, but also to IBD, and if possible also to dementia by looking at the eye. And what we try to use in this case is so-called a multimodal nonlinear microscopic approach for this interoperative imaging. We are using different techniques, nonlinear modalities. In this case, we have pulse laser systems, and there we can go for CARS, coherent anti-Stokes Raman scattering. So we have 2 lasers we shine with at the same time on the sample. We can coherently drive a specific vibration, for example, CH or protein vibrations or DNA vibrations of the sample, and then we can probe with a 3rd laser pulse, and we get an anti-Stokes signal. Since we are using pulsed lasers, we can also do stimulated Raman, 2-photon excitation fluorescent film, as well as SHG, and this gives us a nice variety of information from the sample at the same time. Well, we have developed here a nice Raman device or multimodal imaging device, and the big advantage is that we can use this in a maintenance-free operation way. We can measure quite fast. We can measure quite large areas in a short period of time. This was the device in 2014. This is now the device in 2019. So you can see we even shrink the footprint further. And this allows us, for example, also to go for inflammatory bowel disease. Here, for example, for Crohn's disease or ulcerative ulcerative colitis. And this is what normally is done. You have an endoscopic score, you have the histopathological score, and then this allows you to go for the architecture. You can look at the chronicity, you can get information on the activity. So this is about how is the structure, how many cells are are moving into the epithelium. And here you can see the Mayo score, and you can see, for example, here this is related with already bleeding, and this is the histopathological score. But what is missing is certainly molecular information. And based on our approach, we can go really for a nice assessment. We have CARS, we have 2-photofluorescence, we have SHG, and this we can do quite nicely. And here you can see the crypt structure. But certainly nobody is really interested in learning this new type of modality. So we try to translate this into something which a physician can easily use in an automatic way. And first of all, for example, if you look at the crypt structure here at the Mayo score 0 and here the Mayo score 3, you can see that we get nice information. This is an HE stain. But as I said, we want to have this more or less in complete automatic way. There we would not have any pathological staining, no manual annotation required. We want to have a real-time assessment. And here with this, we're using, for example, these autocoder approaches, really due to the time constraint, not going into the details. But what you can see here is that we have a nice assessment of the crypts. This is done with the pathology. This is machine learning, classical nature. And if you use the autoencoders, you can see with these deep learning approaches, then we get a real direct assessment. And this we can also go for the other samples. And you can see again here the pathological annotation, the machine learning. And we have with the deep learning a really good agreement with the approach. The last topic I'd like to share with you is really something fascinating, the eye as a window to the brain. And certainly, we are looking here with a multimodal approach, which is done in a European project with some colleagues from ZEISS, from the Technical University of Vienna. And you can see here more or less the retina. You get here all these structures. And the nice thing is that we can also get this information without any staining by using Raman spectroscopy. By just looking at, for example, the different clusters we can identify. And by using this approach, we want to go this Raman approach in combination, certainly with OCT, having a fast method combined with a slow method. We want to go for age-related macular degeneration, as well as we want to look at Alzheimer's disease by using these approaches. Well, as I said, we want to go for a combination out of OCT and Raman. And here you have a quick overview about our experimental setup. Using Raman on the eye is something I think nobody has done really before in order to get Raman measurements. The challenging part is certainly to fulfill everything. Yeah. So first of all, we have done some Raman measurements on an isolated human retina. And here you can see, for example, various clusters of the Raman data. You can see, for example, in orange, some clusters which are dominated by some carotenoids contributions. You can see here, for example, in green, some clusters which are then dominated by lipids or by proteins here in blue. And now the question is, can we go also for an in vivo setup? Can we combine Raman and OCT? And here you can see, for example, first of all, this is the white light image. This is the OCT image. And you can see here the crust. If you now overlay the Raman data, you can nicely see this nice correlation between the OCT as well as the chemical information. OCT won't have this really deep going chemical information. And now we developed the Raman device, which is really able to do the measurements in vivo. We have a spot size around 100 micron. We have a very low confocal. We have a low collection numerical aperture. We are using just 1 milliwatt, but still we are able to do some Raman measurements. So we use this setup in order to measure here on this retina. These are the raw data. If we go back and do some data correction, spectral correction, then we can get here some nice information. This is our home build setup. This is the optimal setup. These are the in vivo conditions. These are with the VTech device, for example. You can see that we get beautiful Raman data, and with this we'd like to go also now for in vivo measurements. Well, I'd like to summarize this. I hope I could show you in this short period of presentation that biomedical photonics are really is a key which allows us to go for personalized healthcare. Why? Because we get here direct information, label-free information. We can go for chemical sensitive information. We get morphological information. This entire approach is fast. It's non-invasive. We can characterize the cells. We can characterize tissues. We have just to combine different modalities, but what we at the very end need in order to go for a personalized medicine, we need in order to interpret the data or the images, we need chemometrics, we need imaging analysis, and this is somehow in this combination really nice tool in order to go for this solution. Well, with this, I'd like to thank my colleagues, my co-workers. I'm quite happy having such an engaged team of young senior and young and senior scientists. Funding is very much appreciated, and certainly what is also very much appreciated are the collaborators, especially from the physicians, which opens their lab in order that we can do the Raman data, the Raman and our measurements directly in patient samples or the patients. Now, with this, I'd like to thank you for your attention, and I'm open for questions. Thank you.
Thank you for Professor Jürgen Popp. Unfortunately, he cannot take questions. He just got announcement today that he is going to get his first vaccination now. So I text with him and he cannot join us. As he presented, he is one of the leaders in Raman spectroscopy. As I mentioned before, in the European project of the correlative multimodal imaging, he is providing the Raman perspective on different Zoom levels. Jürgen will come to visit Israel at the end of October during the Young GIF event at the end of October after the holidays. And if anyone wants to ask him any question, you can connect me and I will make this connection directly later on, a few months from now. Can meet him personally again in Israel. From now, we will go to our next speaker that with us today, Professor Valery Tushin, great scientist and good friend. He has many titles, fellow of OSA-SPIE, member of the National Academy of Russia. His main title coming from Saratova State University. And today he will talk with us about a joint project that he is doing with Israel about fluorescent protein plasmon nanoparticles. Professor Tushin, please.
Dear everyone, this is my great pleasure to present a talk today, and I am very thankful to Professor Dror Fixler for inviting me to give a talk on Photonics Days of Israel. So this is a presentation on fluorescent protein plasmon nanoparticle complexes as multimodal optical sensors. And this work was done by a few groups, two in Russia and one is Israel, which are led by Professor Fixler. So this is the outline of my talk. We will talk about spectra of absorption and scattering cross-sections for nanospheres and nanorods. And also we'll talk about field localization maps for gold nanoparticles, then try to quantify field localization and some discussions and suggestions how to use these calculations and modeling. So after that, we will talk about some applications of gold nanoparticles, in particular for optical coherence tomography, how it can be used for mammalian embryo imaging. And some will discuss perspectives of tissue optical clearing method to enhance contrast and signals in the framework of the using of these nanohybrids. So the motivation for this work is to use some multimodal optical sensors to trigger therapeutic effects like photothermal, photodynamic, and using the theranostics concept. And the gold nanoparticles and fluorescent proteins complexes will expand applications of fluorescent sensors, we believe. And these gold nanoparticles or hybrids can serve as vehicles for a kind of logic gates, allowing also the use of several detection methods and at the same time serving as platforms for potentially complex structures. So the synthesis of gold nanoparticle protein complexes promises a significant increase in the efficiency of biomedical application of fluorescent proteins due to plasmonic enhancement of the laser excitation field. The goal of this work was to construct a model and study the main features of the gold nanoparticles near field, since the intensity of this field determines the efficiency of fluorescent excitation. And also to quantify the optical properties and geometry of the gold nanoparticles protein complexes, multi-layer sandwiches structures. Like a method, we use the finite element modeling of the spectral properties of gold nanoparticles using the COMSOL multi-physics commercial software package, especially wave optics model. It was assumed that gold nanoparticles is immersed in initially in an aqueous medium and is irradiated by a plain linear polarized electromagnetic wave. So you see here some results regarding absorption cross-section and scattering cross-section. This is absorption cross-section for gold nanoparticles without any proteins. This is naked gold nanoparticles, this is spherical nanoparticles, and this is dependence of the plasmonic resonance on the diameter of these particles. So you see that we can tune absorption cross-section, which is important for some applications like treatment or heating, and also scattering cross-section. Plasmonic resonance is shown here. Also, it dependence, the varying dependence on the radius of the nanoparticle. And scattering cross-section is important for some imaging analysis. So similar spectra you can find down for nanorods with different aspect ratio, which also showing us that we can tune the wavelength of plasmonic resonance in some limits, rather big limits for this particular materials for gold. So also here you see the tuning of plasmon resonance gold nanoparticles, and criteria here was the position of the absorption maximum. Here is tested a few laser wavelengths and different nanoparticles for spheres and nanorods with different aspect ratio. And you see here the distribution of the gain, of the enhancement of the near field. So the red line, the red color showing the maximal enhancement, and the blue is the low enhancement. So you see here numbers allowing us to predict how the local field is distributed within the particular nanoparticles, and to make a choice to excite the proteins which can be connected around this gold nanoparticle. So indeed, we have to see the field localization. And as an example, we took the different distances apart from the nanoparticle. I would like to remind that nanoparticle now in the water surrounding, and this is the distance from the surface of the nanoparticles, 5 nanometers, 10 nanometers, up to 15 nanometers. And once again, this is different nanoparticles, different parameters, with spherical ones and rods here. And also in this table, you see the range of variations in the field enhancement, which are rather big. You see here, because you say, which correspond to the red color here. And the range is huge for, especially for these particular nanoparticles. And also the right part of this table showing the laser intensity, ensuring the same minimal strength in the electrical field localization zone at distance from the surface. Once again, 5 nanometers, 10 nanometers, and 15 nanometers. And this is the regarding the this type of nanoparticles. So that means that if we need some intensity to get some localized near field or particular strength of the electrical field localization for this particular nanoparticles, we need much more for another aspect ratio, particles with another aspect ratio for nanorods, and also 300 more intensity we need to get the same enhancement, the same near field. So indeed, the nanorods is more optimal to provide such field, which we need to provide excitation of the fluorophores around the nanoparticle. So here you see calculations already for the, but this calculation done for nanospheres, because nanospheres is more suitable for our particular task. Why? Because our fluorophore is working, or protein is working on this wavelength in the visible light, and therefore we have to optimize excitation of this fluorophore, particular fluorophore. And you see here, this is the our sandwich, our hybrid particle, gold sphere here, then some layers, including the pegylated layer, PEG layer, and streptavidin layer, and here we see the our fluorophore layer, red fluorescent protein. So the thickness of the layer PEG plus streptavidin is around 15 nanometers, refractive index about 1.5 nanometer, and the TAG RFP is about 4 nanometers. And these calculations show us that if we compare coated and uncoated nanoparticles, nanospheres, and coated with protein, you see here some redshift. And this redshift should be taken into account when we making such hybrid nanoparticles. So also we have the same tuning of the plasmon resonance for the maximal field enhancement here. And this is our target. We need to have a maximal enhancement for these wavelengths, which are fit to the wavelength of our fluorescent protein. So some calculations showing us or allowing us to optimize the radius of the nanospheres, independence of the protein, fluorescent protein we are using in our work. And this is for uncoated, and this is for coated nanoparticles, and also for two wavelengths dependence, this gain on the diameter. So you can optimize now dependence of the wavelengths you wish to use. So how to make a choice? Indeed, we have to take into account the redshift of the resonance for different criteria. And the final, you can see here that how the behavior of the optimal absorption, optimal scattering across section for the independence of the diameter and the wavelength used, and also for maximal value of the enhancement of the field. And in our case, the optimal diameter is 35 nanometers should be, and which are corresponding to this absorption spectra of the fluorophore. So, and this is the optimal wavelength, which allows us to fit well to this data. So now I would like to show you a few examples of application of nanoparticles, which we used in our work. So this is the OCT system, which allows to see 2D or 3D images of the particular living mouse embryos, and for different concentrations of the gold nanoparticles, gold nanorods in this case, 10, 20, and 50 microgram per milliliter. And this tissues was incubated with the nanoparticles solutions during 3 hours or 6 hours. And this is the resonance, plasmonic resonance curve for these nanoparticles. And this is, you see here 2 examples, before impregnation or before incubation in the solution of the nanoparticles and after. Indeed, this image is much more pronounced, much more, much better than this one. This is one example. And also, if we need to enhance application of the nanoparticles to have better contrast or better in-depth treatments using these nanoparticles, and the light scattering is preventing such in-depth vision or in-depth treatment. Therefore, optical clearing technology can be used, and it is based on the refractive index matching of the scatterers. You see here tissue. This is refractive index modulation. And indeed, we can, if we match refractive index of the scatterers and the background by impregnation and by some immersion liquid, we can provide some less scattering. Indeed, less scattering is accompanied also by tissue shrinkage and dehydration. And all these mechanisms give us less thickness, better ordering of the collagen fibers if it's fibrous tissue, or some other structures of tissue, and also refractive index matching due to impregnation and water goes out from the interstitial space, and clearing agent go inside. And so all these lead to some matching of refractive index and better ordering and less thickness. And you see here example how clearing is working. For example, for rabbit Duramatter, 1 drop of glycerol allows you to have a total optical clearing, nothing seen here, and it can be happened in a few minutes. So one of the example of application of this optical clearing modality is fluorescent intensity images of mouse cancer cells in vivo. You see here what after clearing using the 70% of glycerol, 5% of DMSO, and 25% of water, we can enhance clearing or fluorescent signal much better. And also we can increase the contrast of these images. This is protocol, and another agent like CT contrasting agents or MRI contrast agent can be used as optical clearing agent. And the efficiency rather high, up to 2 times, up to 5 times here, you see. And also contrast is can be significantly improved. Indeed, this can be happened only on some time scale. So another example for upconversion nanoparticles, you see here before injection, after injection, and after optical clearing, we see pretty good signal here. And finally, I would like to show that it also works for cells. And one of the examples shown here, that this is a nanoprobe, you see here, and this is background. And when the background is eliminated due to optical clearing, we can see much better internal structures or organelles within the tissue. So we did some calculations many years ago, how to increase the contrast within the cell using this optical clearing and nanoparticles, and it was recently proved experimentally. So in conclusion, I would like to say that mathematical models are constructed and numerical modeling of the near field distribution of 2 types of gold nanoparticles intended for the designing of effective fluorescent protein gold nanoparticles complexes is performed. We did some numerical simulations, which allows us to optimize these nanohybrids to provide more effective fluorescence. And the low sensitivity of field localization to the wavelength change causes a weak criticality of the wavelength matching within the protein gold nanoparticles complexes. Indeed, we can enhance using the nanorods, we can enhance field up to 300 times in comparison with the spherical nanoparticles. And also tissue optical clearing method allows for a significant improvement of optical image contrast with subcellular resolution using gold nanoparticles and fluorescent proteins. So we are thankful for Russian Foundation for Basic Research and also for Ministry of Science and Technology of Israel for supporting of this work. Thank you for your attention.
Thank you very much, Professor Valery Tushin, for the great talk and to be with us today. What is the situation in Russia? What is the efficiency of your vaccinations?
Efficiency is good. I did it in April, maybe a bit later, a bit earlier. So I already traveling to south part of Russia and hope to go to Israel and also to China in December.
No way to go to China. I'm hardly believe this is not our business now. You present very nice issue of the gold nanoparticles, mainly in the simulation, different aspect ratio and coating. In these days, everyone is very interesting about influencing virus on the electric field. Let's say that a virus will come close to the surface. Are you predict that something will change in the electric field?
It's a good question. Indeed, so we're irradiating our nanoparticle. So indeed, it works like some concentrator of this light, and scattering is localized some hotspots. So indeed, if any biological structure will connect these hotspots, indeed, we can produce something, we can excite something, or hit something. It could be, if we are talking about the COVID, for example, so it's the size is about 100 nanometers, you know. So it's a big one. So,
but it's almost transparent. Maybe scattered is not absorbed, as I know.
Yeah, but refractive index still, like for any biological material, it's not small. It's should be bigger than for water. So we can see some changes. Indeed, now the question of the numbers, and we can imagine two situations when we have one big virus and a lot of small nanoparticles around, because it's rather big, or vice versa. We have only one big nanoparticle and comparison. So it's interaction of two nanoparticles. One is dielectric, another is so it's interesting. We try to model it, as well this situation. But indeed, some changes should be, but maybe not so big.
Yeah. Thank you. Another question is about the shape of these nanoparticles. You did about spheres and rods. What about cubic or triangular? There is a good reason why to use sphere and rod.
For spheres, this is only one reason. So it's very common, easy to produce, easy to buy, and for our particular work now, it is well matched to the wavelength range of the chromophores, which we are using. If we move to infrared, indeed, efficiency should be much higher if we use nanorods or nanostars, for example, because hot spots are more, enhancement is should be bigger. But the problem is only if we have or not such a proteins. If we have, we have a lot of varieties. I don't. So in former time, nanocubes was interesting field, but I don't remember that many groups now working with this such nanoparticles. It's mostly nanorods, still nanorods, nanospheres, and nanostars.
There is another direction of quantum optics. It was a session of yesterday, and they present for a source for entanglement coming from nano triangulars or cubes particles. Silver.
Probably. I'm talking only about the real applications in biomedical biology.
Okay, thank you very much. When are you planning to come to Israel?
So
you're open.
yeah. So I hope maybe next year. Maybe next year.
Okay, we will get another vaccination until then.
Yeah, no problem with that. Yeah.
Thank you very much, Professor Tushin, to be with us today and for the lecture. And stay safe. We had two great scientists from Germany and and Russia. Now we are going to great scientists coming from the industries. You know, our conference of biophotonics and medical is focusing on the industry as well. And I have the honor to introduce Dr. Bernhard Hesse. I met him several times. He visited Israel. He is very active in European projects that the Israeli companies are involved in, Israeli academia as well. He's coming for ex-Polariton company. And today he will talk about cyclotron-based X-ray analysis. Dr. Hesse, please.
Good afternoon, everybody. My name is Bernhard Hesse. I'm the CEO of Exploration, a company based in Berlin. And at the same time, I'm visiting scientist at the ESRF, at the synchrotron in Grenoble at Beamline ID21. Now I want to speak a bit about synchrotron-based X-ray analysis of medical implants for advanced material characterization. Who are we? Exploration, this Berlin-based SME. It's our mission is to bridge the gap from industry and academia analytical demands to technical solutions that are available in synchrotron research facilities. We are in strong collaboration, or actually legally linked, with the company Novitom in France, and together we run through sites, one in Germany, two in France, and we have more than 20 experts in our group from the domains of physics, chemistry, biology, and computer science. We are mainly focusing on computer tomography, X-ray spectroscopy, and X-ray diffraction. What are X-rays? Today we already heard a lot about visible light. It's a visible light wavelengths, let's say 0.5 micrometer to 1 micrometer, I mean order of magnitude. And the energy of visible light is about 1 electron volts. In X-rays, we have energies much higher, in the order of hundreds of electron volts or even several thousands of electron volts. At the same time, the wavelengths of these X-rays are much shorter, in the order of angstroms or nanometer. And because of this very short wavelengths, high structural resolution or high spatial resolution can be obtained. For example, X-rays are used to discover the crystalline structure of this very annoying SARS-CoV virus, or in this case, the spike protein. It can also be used for radiography, for example, or computer tomography. Because of the high energy, it can pass easily through very dense and absorbing samples, such as medical implants or bones. The interaction of X-rays with material are on the can take place on inner electrons, and thus it's enabling for very simple or very straightforward elemental or fingerprinting of elemental composition. Furthermore, with X-ray spectroscopy, we can assess crystalline structures, oxidation stage, and such. In this case, you see here there's a cell filled with all kinds of metals related to an implant exposure: titanium, tantalum, zirconium, nanoparticles. This cell is about 20 microns in diameter, and if we're now interested in the titanium structure, we can even distinguish if it's in rutile or crystalline, rutile or anatase form. X-ray sources. I think that most of the people think about scanners that can be found in laboratories or on X-rays related to when someone breaks a leg or needs a computer tomography. This is how it then looks like. Where we work, it looks a bit different. A synchrotron facility is a very large particle accelerator. It should be not confused with this accelerators used for basic physics like CERN. The synchrotron is really used for application for like, let's say it's like a microscope, we can say. So in size, it's bigger than any football stadium found anywhere in the world. In the synchrotron, electrons are circulating along the storage ring, and they pass through bending magnets or undulators or magnets. They produce X-rays that are then used for further investigations. A synchrotron is a photon source. It offers unique properties in terms of brilliance, which is like intensity normalized by some spectral width of the wavelengths, and it delivers an intensity that is 100 billion times brighter than X-rays produced in hospitals or laboratory sources. So we can call it a super microscope, I would say. Now coming to the topic, let's say, we wanted to speak about implants, implant materials, and what's the problem about it. So generally, there's many implants placed into human bodies in the world, let's say. Just for dental implants, to give you some hard numbers, it's about 12 million implants placed per year in the world, and approximately half of them develop inflammation at some point and need further intervention. These medical interventions are associated with, of course, negative impacts on quality of life and high costs for the healthcare system. Just in Germany, per year, there's, let's say, around 100 to 200,000 primary implantations of hip endoprothesis. And in the same period, there's about 20 to 30,000 revisions of primary hip implants in the same time. So there are still some problems, let's say, with this material. How can these problems look like? Here you see a drastic example of a failed hip implant. You can see that there's fragments of the screw all around the show. There is particle exposure. You can see osteolysis of the bone tissue. So this patient is probably suffering a lot, and of course it has to undergo further surgery. And the aim of, let's say, our previous studies and of our services that we provide is an assessment: is there an exposure of implant-related material in human? Even if the implant failed, like in this figure, it's very obvious, but we want to know, is there also some exposure of implant materials, even if they do not break, but just because they're around. And then how does the exposure look like? Is it nanoparticles, microparticles? So what's their size, shape, oxidation state, colocalization? What's the kinetics? And what does the exposure eventually do to the tissue or to the patient? So is there suffering of oxidative stress, cell damage, eventually even tumor formation? To assess this exposure, X-ray fluorescence is a tool, or is a technique we use a lot for this. So we have our synchrotron source providing the X-rays. So again, the electrons circulating in the storage ring, when they pass through this magnets called undulators or insertion devices, they produce this high energy X-ray beam. They go through a monochromator, through focusing optics, and can then be, let's say, focused on the sample in very small spot sizes, such as tens of nanometer. Of course, they can be also larger, microns or millimeter size, but let's say high resolution is something that is relevant for this implant exposure assessment. Then the sample can be moved through the X-ray beam, and for each position, the fluorescence spectra can be collected. The fluorescence spectra can be deconvoluted, because here every basically peak is associated to the presence of a certain element, titanium, phosphorus, iron, and so on. And so for each point in the sample, we can have the full composition of the sample. Of course, we can also, in some cases, put a transmission detector and then collect, for example, the diffraction signal. So then in the same spot, we have the fluorescence information and also the diffraction information. And the diffraction information gives insights into the crystalline structure, mineral properties in bone, for example. How does such an X-ray fluorescence map actually look like? Remember, each point that you see in these very big maps are actually based on the, let's say, deconvolution or the analysis of a spectra. So it's very big data. In the center here you see a histological slide with the bone in the upper part and the bone marrow in this region where the white arrow points. And what we see in the fluorescence data now is that there's a high exposure of cobalt and chromium particles in this bone marrow. It's very relevant, because in bone marrow there's the formation of blood and immune cells and all kind of things that are very, very relevant to, let's say, human well-being, let's say, potentially. And so this kind of exposure, or let's say the assessment of this exposure, is the first step. And of course, in a later stage, we have to understand what does it do there. We also looked at different implant materials and different combinations, and even together with cement that is sometimes used to hold the implants in place. And we always see an exposure of implant-related particles around the materials. Regardless, here it's about zirconium. Then there's even nickel-based, or not nickel-based, but nickel-containing materials, or titanium. containing materials. And all the time we see exposure of particles. Here's an example for a very high resolution imaging. So nano X-ray fluorescence with 60 nanometer step size. We have imaged one big cell, 20 micrometer in diameter, which was filled with nano and micron sized different elements or metals made of titanium, tantalum, zirconium. And then for titanium, for example, we could even do spectroscopy to find if it's like, let's say, in rutile or anatase crystalline form, which has a different meaning for the toxicologists. So far, I showed you this elemental exposure assessment, but of course, it's very interesting or relevant to also look at the, let's say, to look into the 3D structure of the implant materials or of the bone tissue when they are exposed to implants, for example. For this, again, we use synchrotrons, put the sample into the beam, rotate the sample, and for each rotation, we collect a projection. We can then back project and have a, let's say, a real or have a, let's say, a 3D image of our sample. Here you see an example of magnesium-based implant materials. Magnesium is a very promising material because it's, let's say, it's tolerated by the body, or let's say not associated to any risks. The magnesium itself, and magnesium is corroded or degrading over time. In the beginning, magnesium has a very good mechanical competence. And over time, when the bone is taking over in a defect region, for example, the magnesium corrodes or degrades. And in the final stage, the magnesium is completely degraded and the bone has fully taken over the region formerly containing the magnesium. Here you see a virtual slice through a 3D scan of such a magnesium screw at the already progressed corrosion state. And you can see, and keep in mind, this is just one virtual slice. We have thousands of them because in one scan we reconstruct really a 3D volume. But you can see here that the signal to noise is just great. And in the, let's say, metallic phase of the screw, you can see you can discriminate the metallic magnesium from corroded magnesium. Corrosion fronts, we see the bone tissue around there because of the, let's say, high sensitivity to the gray value. We see young bone tissue. We see soft tissue, all at the same time with very high resolution. So it really reminds us on histology, just that this is 3D imaging modality. Here's a comparison to a lab CT, a standard lab CT scan of such an element, and you can see that the signal to noise is completely in a different world, let's say. I think that the resolution was a bit different between the two scans, so maybe it's not a 100% fair comparison, but nevertheless, the signal to noise, just due to the high flux in synchrotrons, is of course just plays in a different league. So we do support our clients with preclinical or with data for preclinical studies. For example, in this magnesium-based degradable implants, we quantify the metallic phase or the corrosion rate over time. We can quantify the tissue response. We can visualize it and and then deliver it to our clients or customers. Generally, we have in our company we have a strong expertise in biomaterials, in particular for bone imaging. For bone, we have strong experience in imaging from the, let's say, on the organ level. In this case, it's the red femur, about cortical thickness, trabecular distribution, vessel porosity, vessel network, but even down to the micron scale. So here you see small things are the osteocyte lacunae, small cells, few micrometer in size, and these cells are even connect to each other through a very complex called canalicular network. And one of these canalicular channels are just few hundred nanometer in size, and we can, with nano CT based on synchrotron technology, we can do this at 50 nanometer voxel size in 3D and then compute the network properties of these very fine networks. Of course, preclinical studies are done in, let's say, small animals, mostly or very often, let's say. The problem with animal studies is, of course, there's some ethics concern, but also in terms of cost, it's expensive. And many of these animal studies are difficult to translate into, let's say, into human, or let's say it's still a challenge. So it's let's say there's a need for alternatives, and it goes into this 3R, so reduce, replace, refine, let's say topics. And ideally, we would like to acquire samples with patient-specific data, so let's say human samples, and then analyze native material and transform these findings into in vitro models, and then build a reliable tool to ensure biologically representative function and reproducibility. And for that, we are involved in a project with Charité Hospital here in Berlin and the University Hospital in Greifswald with Janos Schoen mainly, who has an organ-on-a-chip model that is basically working such that he gets bone tissue from patients, basically, or from surgery. These bones are decellularized and then exposed again to relevant cells from plasma, and they are put into a microfluidic system, and basically the microfluidic system enables this tissue to, let's say, to maintain homeostasis and to do remodeling and all the things. And basically it's a bioreactor, right? And in this bioreactor, we can then study, using computer tomography, for example, bone formation and bone resorption over time in basically human tissue, but in an organ-on-a-chip model. So we have really a controlled sample environment, and we can then study, for example, the impact of implant exposure on bone remodeling. The device that we develop basically works such that we have a sample in the chamber, and we can have it in a controlled liquid environment, and of course it can be used for many different applications. So we can measure 3D with a high spatial and also with a high time resolution in liquids. Also in implants, 3D printing is a very upcoming topic. 3D printing of titanium-based alloys or Inconel-based alloys is something that's going on. But here also, it's let's say the porosities are, let's say, our well understanding of porosity and surfaces are very crucial. And with synchrotron CT, we have sufficient energy and resolution to let's say 3D image like samples that are in the order of centimeters, even of this very dense and absorbing material, to study the, let's say, quality control of such materials. And we believe that such a high surface as shown here may have also, or maybe also linked to some exposure of the material into the body if it's brought into the human body and used for implant materials. With this, I would like to conclude my talk. I thank you for your attention. I looking forward for discussions or questions if you have some. And finally, I want to show you a small video, how it looks like when we receive a sample and bring it to the synchrotron. Scan it there.
Thank you, Bernard, very much. The podium is open for question. I would like to ask one. During the last more than a year, I assume that you got new questions that deals about the new events and things that happen. Can you share with us something that your company can help scientists or other people to solve questions that have any kind of connection with the pandemic?
Related to COVID, we haven't done any research. That's not our topic. But there's a lot of synchrotron stuff going on. I mean, for example, computer tomography was applied to image lung tissue of COVID patients at one of the facilities where I'm a visiting scientist. to image the blood vessels and let's say how they get tightened with the disease.
It's what exactly I saw. You present the vessels, blood vessels. So you are not working on blood vessels, are you?
We are working on blood vessels, but not on those in the lungs, let's say, that are related to COVID.
Okay, I understand. During your talk, you provide the idea of the micro-CT and the cyclotron and the different wavelengths that you can provide. When we are talking about imaging, no doubt that this is a very straightforward technique. But in case that we are talking about integrated photonics, do you have anything that can be integrated?
Well, of course. I mean, I think that when I showed, for example, the organ on a chip, the bioreactor, I mean, we bring this to the synchrotron and we do our computer tomography there, 3D imaging. Of course, it would be super nice to couple this device to, for example, Raman, and then see parameters like LD, like some cell viability parameters, for example, to couple this to the, let's say, remodeling of bone and so on. We haven't done this, but I think that's, I mean, I think in the audience are for sure people that that could give feedback and maybe would be interested in collaborating on this.
Definitely. So this is a podium that I just want people to know that you are a very great partnership for this kind of collaboration, joint work, and mainly joint submission to the New Horizon program. More specifically, I know about programs that are going to be announced about integrated photonics, and people want to sense gas and some kind of biomedical parameters. What kind of biomedical parameters can you provide, measure with this kind of organ on chip?
Well, the parameters that are obtained there are basically after we do the measurement. So that's then standard lab things, let's say. But what we are pushing in terms of technology is time-resolved computer tomography. So we have, let's say, a series of 3D imaging. And with computer tomography, we get, let's say, mass density. So it's interesting for everything that is, let's say, alive, like tissue growing and when there's a supply of blood and so on. But of course, it could be nice to link, for example, LDH, all these kind of parameters. Yeah, that would be interesting.
So do you have experience in this kind of questions?
My colleagues do have. It's not so much my topic. I'm more on this, let's say, structure side, so 3D structure and elemental exposure and spectroscopy in terms of crystalline structures. Not so much on the let's say, cell and enzymes and this kind of things.
Great.
But it could be coupled.
Yes. What is the situation in Germany now? You are in Berlin, yeah?
I'm in Berlin. It's just last week, I think they opened again the restaurants on the outside only. So, but it's getting much better. I'm already vaccinated, so I'm one of the lucky ones. Yes.
Nice. Yeah.
Yes. We are all looking to Israel, and you guys, you are way ahead of things. Yeah. So it's very nice.
Looks good. Currently looks good. Hope it will continue. Thank you very much, Dr. Bernhard Hesse. And hope to see you face to face again, as we are frequently doing.
I hope so too. Thanks.
Before going to the next speaker, we just got a late question to Professor Tushin. Questions that arrived for Samuel Yerushalmi. He talked about something more general about cooperation between Russia and Israel in the nanotechnology field. And I can tell that there is already collaboration between Russia and Israel. It's coming from different directions, industry and academia. It's not limited to nano per se, but there is a specific topics in what just Professor Valery Tushin presented. It's some kind of collaboration like that. And in the optic and nanophotonics, it's something that it's ongoing. Israel, it's not investing anymore in the nano per se. We are looking for more general topics. We combine different topics like sensibility, energy, quantum technology with photonics. And by building a bigger umbrella, there is a lot of collaborations between these two countries. Here we have Professor Tushin with us. Can you add more about this question, please?
So we will be happy to collaborate indeed in biophotonics in general. So it's not limited to nanophotonics as well. So we are working a lot, and I believe now in our country we have two foundations. Russian Foundation of Basic Research, which has now closed or joined with the Russian Science Foundation, unfortunately for us. But we are waiting that some, especially collaborating international projects will be supported by, still will be supported by Russian Russian Foundation for Basic Research, as we have between our groups. So Russia is open.
Samuel Yerushalmi asking, and you are the great person to answer. You are coming from the academia. You are a member of the Russian academia.
Yeah,
Is
yeah.
there any perspective on looking on nano per se, not nanophotonics? General nano, it's material science, 2D materials, and more.
Yeah.
Is it the Russian academia looking for this kind of specific topic? Is it?
Yes, yes, I think so. Yeah, it's Russian Academy of Science is interested in nanophotonics, not only for biomedical science, indeed. So, but I'm not ready to discuss right now, but I know that in Russian Academy of Science report, there were a lot of the papers or reports devoted to from different institutions devoted to the nano, but it's mostly sensors and for chemistry, for biology, and so on. So I think it's still.
Yeah, it's still relevant and hot topic. The sky is not yet the limit. So for Mr. Yerushalmi, for your question, the answer is yes.
Yes.
Thank you very much, Valerie, to coming back. And now we are going to our next speaker. From Germany to Russia and Germany, we are back to Israel. The last two talks will come from Israel, but not from the regular universities, the 6 universities that we have. In Israel, we have several colleges, and one unique college is coming from the Jerusalem College of Technology, JCT. And from there, we have Professor Salman Noach. He will talk about widely tunable narrow bandwidth laser for medical application. Salam.
Hello, my name is Salman Noach, and I'm from the Jerusalem College of Technology. And thank you for giving me the opportunity to be part of the IL Photonics Days. The topic of my talk will be a widely tunable pulsed narrow bandwidth thulium YAP lasers for medical application. The outline of my talk will include a brief introduction about 2-micron laser application, laser requirements and design consideration, the tuning method that we used, our laser performance, and I will do some ablation experiments and conclude with a summary. In recent years, 2-micron lasers based on thulium-doped crystal have gained growing interest. In many applications, there is a need of pulsed lasers with sufficient energy per pulse with a narrow bandwidth. Between the application, we can mention remote atmospheric sensing, free space optical communication, in the scientific field, pumping source for mid-IR lasers, and the material processing for plastic welding or marking. And the medical field is one of the main growing active area for 2-micron lasers, mainly for selective microsurgery, evaporation, or injection of a tissue. Why 2-micron is interesting for laser tissue interaction? Actually, most of our human tissue is made of water, and this is a favorable absorption in water. This wavelength has a favorable absorption in water. It also an eye-safe wavelength regime meaning that it's less harmless while working with it. It has a coagulation effect that suppresses potential bleeding, and this is an advantage when you're doing a microsurgery treatment. And the delivery of the beam can be used with this regular commercial communication fiber compared to a UV or CO2 lasers that demands unique fiber or a special system based on mirrors to deliver the beam. In this slide, we can see some medical treatments that needs 2 micron laser sources. Part of the application need is CW lasers, part of the application need pulsed lasers, and the ability to tune the laser can be improved each treatment. And as far as we know, there wasn't such a tool, which is a pulsed tool with a tunable, with a narrow bandwidth that exists in the market. And this is what gave us the motivation to develop such a tool. Here we see the absorption coefficient of water that is very similar to our tissue, and the penetration depth versus of the wavelength. And we see that there is 2 peaks around 3 micron and 10 micron, and also a peak around the 2 micron. But although here we have a higher absorption coefficient, but if we see the penetration depth, we are in this wavelength, we are very limited in the penetration depth between some up to tens of microns. But if you want to make a microsurgery tool, you have to penetrate more than that. You have to penetrate between some hundreds of microns, close to 1 millimeters or more than that. And because of that, we prefer to work at this spectral area that enable us a higher penetration depth. And also you can see that there is a meaningful difference in the absorption coefficient versus of the wavelength. So if you develop a tunable source, you can control the penetration depth by controlling the wavelength. So this is the idea. So a laser, a gain medium that emit nearby the absorption peak of water is a thulium YAP that emitted 1.94 and has to be pumped in 790 nanometers. And recently there are very good laser diode at this wavelength. And with the improvement of the laser diode, we can improve the laser performance. So our research goal is to develop a pulsed tunable narrow bandwidth thulium-based lasers near the absorption peak of water. We want to develop a pulsed laser because it is well known that the lateral thermal damage to the tissue is caused by if you use a CW laser. But if you use a pulsed lasers, you decrease the lateral damage significantly. And this is something that we want to avoid, the thermal damage to the tissue. And because of that, we need to develop a pulsed laser instead of CW lasers. We want a power target of a millijoule level in order to be behind the threshold of making an ablation. We want to check a silica fiber delivery, and we want a compact size and a low-cost laser module. And we want to investigate the laser interaction with the tissue. So our main design consideration was to work with the solid state lasers because of stability and mature technology. And we want to achieve, as we said before, few millijoules per pulse. And in fiber laser, the rank is 1 millijoule, just 1 millijoule. We use a thulium YAP crystal since it's emit close to the absorption peak of water. And we need to do a thermal management in the cavity in order that the component will survive with the high power. We choose to work with the diode end pump configuration for a high beam quality and precise tissue ablation. We want to achieve a tunability while remaining simple, and we want small dimension and low cost. There are many techniques to achieve a tuning in a laser. We can use a prism, layout filter, which is a birefringent plate. Relatively new is the volume Bragg rating for this wavelength, and a Etalon plate. In this case, we choose to work with Etalon plates because of its low cost, no polarization dependence, it's a narrow bandwidth, it can be uncoated, so it can live with the high power. It has a simple alignment and it's limited, but the disadvantages of that, it's a limited tuning range, depends on the thickness of the Etalon, and it's need high polishing, relatively high polishing requirements. So the Etalon is typically made of transparent plate with two reflecting surfaces, and Etalon is widely used in lasers and spectroscopy to control a wavelength selectivity of light. And using one Etalon give a trade-off between bandwidth or the free spectral range. The thicker the Etalon, you have a small bandwidth with a high transmission, and the thinner the Etalon, you increase the free spectral range. So our novelty was to use or to put in the cavity two Etalons, and each Etalon gives a degree of freedom in the bandwidth or in the free spectral range. So here we see that the thinner Etalon determined the free spectral range, and the thicker Etalon determined the bandwidth. Now, if we fixed the thicker Etalon, the thicker Etalon, and rotate the thinner Etalon, each time we can control the wavelength that has a high transmission, 100 transmission, and this wavelength will be built up in the laser. So if I will now rotating the thinner Etalon, we see that each time different wavelength will be with the 100% transmission, and this is the wavelength that will build up. Here we see that it's 1.91, and when I rotated the thinner Etalon, now it's 1.92, sorry. What was the state of the art in a tunable laser? Here we can see some of the works that has been done, and we see that there is a relatively high tunability from tens of nanometers to 239 nanometers. But most of the works done with the CW lasers. So our laser configuration is linear resonator made of the pump diode, the pump optics that focused on the crystal, an active Q switch, and the two Etalons in the cavity, one that control the bandwidth and one that control the free spectral range. And for the performance, here we see the energy per pulse versus the absorbed pump power. And all the measurements was taken in a repetition rate of 1 kilohertz. Maximum energy that we achieved was 2.3 millijoule. And we achieved a slope efficiency of 31%. And almost there wasn't a change in the loss if we used the Etalons compared to the free running lasers, compared to other tuning components that increase the loss. From the spectral point of view, the free running lasers without Etalon has a 2 nanometers full width half maximum of bandwidth. And by adding the Etalon, we decrease the bandwidth to 0.15 nanometers. On the temporal performance, we reduce the pulse duration reduced from 160 nanosecond to a 29.5 nanosecond in the maximum absorb pump. And here we see the shape of the temporal pulse at the maximum pump power. And here we see the results of the tunability. We achieved the 35 nanometer tunability, limited by the thinner Etalon thickness. We achieved the max energy per pulse of 2.3 millijoules. And at the edge, we achieved 1 millijoules at the higher wavelength of 109061 nanometer. So this is the first time that the continuous tunability was achieved, and these results were published in January 21 by our group in optics and laser technology. From the quality of the beam, we measure the M-square of 1.4. We do a 2D scanning with a pinhole, and after that, in a different Z places on the Z-axis, and we made a Gaussian, fit to a Gaussian, and we achieved these results. Now about the laser tissue interaction. The laser tissue interaction depends on with the molecular type, the power density, and the illumination duration. We build this setup to deliver the beam to the target, to the duodenum tissue with a fixed wavelength of 1936 nanometers. This was a CW laser, and this is the tissue. We used an exposure time about 1.5 seconds, and with the radiation was 500 watts per square centimeters. And the results of the ablation, we have a good penetration depth, 1 millimeters in the penetration depth. What we see in incomplete ablation, and we see a thermal damage on the surfaces. This is because of the nature of the CW operation. Here we investigated the different penetration depth versus wavelength, and we achieved the results that the higher the absorption coefficient, it's the less penetration depth. And here we see that we achieved a 1050 micron using a 1936 nanometers and a 1190 micrometer penetration depth in a wavelength of 1945 nanometers. So this is give us the potential of this method, and by using different wavelength, you can achieve a different penetration depth. These results done with the CW lasers, and we are going to make these experiments also with the pulsed lasers in the next future. From the fiber delivery, we want to couple the laser to a fiber, and we use the regular communication fiber that is a good transmission in the 2 micron regime, the low OH fiber. And we see that we achieved the coupling efficiency of 75%, and we have at the output of the fiber more than 1 millijoule. That is the threshold of making a good ablation through a tissue. And at this level, we have a peak power of 40 kilowatt, well, the maximum of the peak power was 80 kilowatt but at this peak power, the fiber survived and wasn't damaged. So we have to check what is the maximum peak power that this fiber can handle. We can use a higher core diameter if you want a higher peak power. So our future plans is to finish the medical study in order to achieve statistical significance. We want to bring this live prototype to the engineering prototype, and we want to collaborate with the motivated groups in this field to develop this tool. So to summarize, we demonstrate the first time with narrow bandwidth tunable mini-Joule level 2 YAP laser. The tunability and the narrow bandwidth achieved by using 2 ettalons in the cavity. Each ettalon was responsible to one thing, or the narrowing or the free spectral range. And we introduced the concept of the development of a medical laser scalpel with controllable cutting depth based on the different absorption coefficient versus wavelength. And we showed the fiber delivery probability can be done. So thank you, and I want to thank the funding from the Israeli Ministry of Science from this project. Thank you very much.
Thank you, Professor Noach, for this interesting talk. If I can summarize the innovation of your talk, it's a new laser type with capabilities to tune it in few hundred nanometers, tens of nanometer, that can achieve a new way to go to the tissues as a medical science. You mentioned almost at the end of your talk that you are looking for collaborations. Collaborations of what? In the laser fabrication or in the application? What kind of collaboration? It's interesting.
The pulse duration with the interaction of a tissue, it's a very famous question. And if we want to make a good ablation results, we have to investigate it, that if we are still in the nanosecond scale, what we can do with the tissue, because there is application that demand femtosecond or picosecond, and we want to verify what will be suitable to nanosecond treatments. And so collaboration with the interaction with the laser, tissue interaction actually, and also with the fabrication of the laser in the future.
Understand. You showed in your results section the tunable issue, different penetration depths on tissue. First, what was the type of the tissues that you present? Second, how you measure the penetration?
We made some histological measurements, and the histological expert tell us what is the penetration depth. He signed it in the slide of each slide. So because of that, we know the penetration depth. He actually did it because he see the damage to the very different things that there is in the tissue, and it was this results was in the duodenal tissue.
What is the duodenal?
Mea gas. It's different.
Okay.
In the
so
gastro field.
In the gastro. Okay. So
yeah.
It starts few centimeters below the stomach. How your laser arrived to this tissue?
In the future, you can do it through a fiber.
Endoscopy. You will do endoscope. At the end of the endoscope, we will have your laser, and then you will do the ablation in this specific place.
Yeah, and because of that, we want to actually deliver the laser through a fiber. And what is very unique here, it's just you can use a communication fiber that is a very cheap
it's
fiber.
simple and cheap. So okay, you will use endoscope, you will do a treatment, you need to add an imaging because you need to know where to make the treatment first.
Yeah, but in endoscopy, you have such cameras.
So you don't have any evidence of the real penetration depths. You can see only the histological medical doctor telling you it's ablate this point, but maybe it's makes the ablation not through the penetration. It's hit one tissue, it goes to another tissue, and so on.
No, because of that, we said that we need much statistical results in order to make good evidence. What is the level of the energy that you can put, and what will be the penetration depth here?
Okay.
We are just in the beginning.
Thank you. Yes, it looks promising.
Thank you very much.
Thank you very much for this talk. Have a great day. And the last speaker in our session today is coming from the Vulcani Institute, Dr. Iftach Klapp. Vulcani Institute, it's a very unique institute in Israel. It's the main and large place for agriculture, plants, and other research in this field. Today, Dr. Klapp will talk with us about very interesting and important topic of real-time monitoring for organic matter, and he is using different optical tools like fluorescence spectroscopy and other tools like algorithms and neural networks. So, Dr. Iftach Klapp, the podium is yours.
Hello, everybody. My name is Iftach Klapp. I'm a researcher in the Vulcani Institute. Today, I will talk about our work with the title Towards a Real-Time Monitoring of Organic Matter in Irrigation Water using fluorescence spectroscopy and convolutional neural network algorithm. We have few collaborators with us, and the work was carried out by Sergei Sinicha, which is one of my MSc students, an electrical engineering student in Tel Aviv University. Okay, the background, I mean, Israel is a semi-arid country and use the recycled water to support its agriculture, and actually use more than 500 million square meter recycled water annually to this cause. And one way to use this water is by making a mixture of clean water and recycled water. And since, I mean, we use a lot of this water, there's a need to monitor that, because such a water coming from wastewater can bring in faeces, originate bacteria, and we need to know if there's some error in the process. So we have this goal in our mind to detect a break of dissolved organic matter into the irrigation system. In addition, we would like to know how big is this dome concentration. In the general view, I mean, such a work is giving some advantage to the general research around the expected reducing in water resources for humanity in the coming 30 years, which it is expected that we will have an increase of water demand in 20 or even 30%. So on the right, I present few fluorescence signatures. You can see, I mean, there is a difference between, it depends on the concentration of the submaterials, and these submaterials divided between the TLF, the tryptophan-like fluorescence, and the HLF, the Homic-like fluorescence. The TLF is associated with the tryptophan amino acid, and it's capable of locating the existence of proteins, though. The HLF is associated with the omic acid, and it's associated with materials coming from the ground. These fluorescence excitations are in the best response to 280 nanometer and 350 nanometer. And measuring, we would like to make a system working in the outdoor And on the right, I present, on the top right, I present in figure A, the fluorescence response of tryptophan in double distilled water solvent. And you see that as the fluorescence, as the concentration here on the side is rising from 2.2 part per billion to 500 ppb, we see that there is a rising in the response. So it's good for us. However, on the figure B below, I present what's happening in a specific concentration, what's happening when we change the temperature, the surrounding temperature, or the environmental temperatures, and you see that actually the response is lowering as the temperature is rising. And in the field, we have a response that it's originate from both changing in concentration and in temperature, and we need to resolve it. So this a nonlinear process and required for some algorithm. So we develop optical and algorithm system, and for that we needed for measuring of water in field condition and water coming from irrigation reservoir, but we cannot take the optical up to the field. So we build some cycling mechanism that will allow us to bring the field to the lab. So outside the field, we build a tank that's working in circulation, and this tank on one of the pipe, we build an optical chamber that we design, and we add another few meters such as conductivity, temperature, and flow that give us information about the environment. And through this optical chamber, we illuminate excited illumination in UV as required, and measure the transferred illumination and the fluorescence illumination. The fluorescence illumination requires us to build a spectrophotometer, which is very sensitive, and need to measure the fluorescence, the entire spectrum at once, because the water are running in about 30 liters a minute. The entire thing was connected to a control, and so the environmental aspect or part of the system is outdoors, so it's subjected to environment. And the spectrometer we place inside the lab for the sake of save them from I don't know, some damage, and because it's very expensive. And inside there is this cabinet was built around these meters because of the safety issues with the UV, and inside we designed the UV sources connected through fiber optics to the optical chamber that we designed, and the reading from the optical chamber is done also, through some mechanism to fiber optics and into the spectrometer. The optical fluorometer was built as a modified Kazerni-Turner arrangement, where we add some arrangement to filter the Rayleigh scattering that penetrate into the fluorescence measurement, and also some changing filters that serve us for the sake of changing illumination source. And our array of detectors was a PMT array, photomultiplier array, and that gives us a high sensitivity sensor that can make a measurement of the spectrum at glance, and it fits to a dynamic system. So we have a lot of challenges in optical design. I won't get into all of them. Here I present that, the overall, we have some sort of response in the filter, and here I present the response to a series of calibrated LEDs in the required measuring range. And in dashed, you see the response of our system, and in the solid, you see the measurement as they done with the calibrated spectrometer. So as you see, there is some shift, and this shift is changed. So we learn this shift and process some sort of calibration formula. And here is after the calibration, we reduce the shift to down 2.4 nanometer, which was less, 1/3 of our spectral resolution. Below, I present our measurement against the measurement of a lab spectrophotometer. Dash is our measurement, in solid the lab spectrometer. So we were very close and close enough. In addition, since we are doing with the system learning system, we can compensate for any other changes if required as part of the learning quantity. So we bring the field to the lab. We actually went to the field and with this tank, fill it with all kind of water, pump it to our tank, and start running an experiment. So between 48 to 72 hours each. So this is a typical result. Here I only present on the right the temperature changing, and on the left the tryptophan or the fluorescence change. So in that point, after calibrating the system, see that it's all work, we start dome break detection. So we add some dome. Here we took milk as our dome source because we can calculate how much tryptophan actually is. And we said that we can actually double the tryptophan level. And as you can see here on the right, in blue is the natural dome in the irrigation water, and in red and green behind, above the threshold, we see the response. So we see there's a clear response, and we could actually measure much more sensitively. And later on, I'll talk about how to increase the sensitivity even more. Here is something that can be solved with hypothesis testing. Okay. So one interesting finding was that the vanishing response. Here I present. X is the response in time, and Y is the response in the response of the fluorometer, our fluorometer. And the measures are of the maximum response for 280 nanometer excitation and to 340 nanometer excitation. As we can see the jump here because of the adding dissolved organic matter instantly. However, we could assume that there's some sort of preservation of mass, and so that we will have the tryptophan with us, and the response until it will, that will last for a long time. But eventually what we see, it's actually decay with a constant of 40 minutes. And in addition, in the next day, we see actually that it's rising out of itself. So what is happening? So what we believe happening is that actually there is also, our system is dynamic. It's not just a tryptophan in dissolved organic matter in a double distilled water in the lab. It's also, we have bacteria in the water from our basic metrics, and this is also changing, and due to the temperature that's changing in this test. And also some tryptophan that was dissolved now is entering into bacteria, so the interaction of light of matter is changing. And also there's some bacteria that's dying, and the tryptophan is changing also, so there's another source of changing. And so the overall interaction of light and matter is very complex, and we investigate of that forward. Okay, so we discussed that we can recognize a dome break, but the question is what is our sensitivity range. In the previous slide, I showed that we actually doubled the tryptophan level. For 40 ppb and double the level. So saying we have about 20 or 40 ppb active material dome or fluorescence materials in the dome. But we want to detect lower levels, levels like 2 ppb, 5 ppb. So we thought about that we can do that probably with by developing a neural network. But neural network required for information, not required for data set, and data set is very easy to measure in the lab, or easier to measure in the lab. However, in the field, we don't control the weather, so how can we mimic the temperature or the velocity change and etc. So what we thought that it will be best if we find some scheme that we can actually take information measured from the lab and transfer it into, I mean, what we learn from it to the field. So, I mean, we have few problems to do that. First, I mean, we have measurement in the lab of tryptophan, and we didn't have much of the measurement of omic acid, because omic acid, unlike pure tryptophan, omic acid are the signature is changed from one material to another, and there is no such a general response or that can mimic quite well. So we actually took the statistic of the water we measure of this peak, and we made some sort of augmentation. In addition, the SNR of this outdoor system is lower, and the spectral resolution of the outdoor or the field system is lower. So we need to make some modification for the signal, and all in all, we get a data set. So we check few architecture. First is, since we want to have a method that can actually use the information learned in the lab to use in the field, we need some intermediate information that is common both to high-level spectra and later on to a lower level spectra that would take place this one. So we suggest an encoding step that encode this high-level spectra to a lower dimension Z space, and this, I mean, and this Z space now is learned to, and we learn the regression relation between this low dimension Z space to our concentration. So this part we can take, we can teach from the lab information, and this part we can is changing when we change the spectrometer. In addition, we check other standard, more standard approaches, saying a neural network that is connecting the spectral and temperature to concentration. This is still in convolutional neural networks and fully connected regression process. So we were most found with the ER, the encoder regressor scheme, because of we can actually transfer information from the lab to the field, and this training is done because we are reducing the high level information to a lower dimension information Z. This is done. We need to stress the Z space such that it will be sensitive to different combination. So this was done by training the entire network twice and stress the difference from the difference of two different inputs, stress the difference in the output, so to maximize the sensitivity of the Z to the input. This scheme of stressing and comparing these two inputs and the output is named contrastive loss. This is the loss function we use. In addition, we of course demand that the estimated concentration will be as much as possible close to the known estimation of the training set. This is done, I mean, both sides of the curve. Afterwards, we have this information and this train set, and we use it for the system. I mean, standard measurement. We measure. We have three data sets we test. We test the information as they come from the lab. We test the test after reducing the SNR and the resolution, and we test it after augmentation. We test above is three methods of the known from the literature, which are linear, and they did very bad results. I mean, with hundreds of % error. And below them, that is the method of the coming from the neural networks, and they all were very good actually, with close to 10, sometimes a little bit less than 20% error in the average. However, and here on the left, I present the training set, the validation set, and the test set. In the x-axis is the actual concentration, and in the y is the prediction. And you see it's almost on a straight line. It's very good in all steps of training for all different temperatures. However, when looking on the 2 ppb to the range of this low ppb, the test set of 3 ppb, you see that only the ER is actually making good prediction of the low concentration. So we find out that the ER is actually the best solution when we want to detect as low as 2 or 3 ppb resolution. So finally, as I summarize the lecture or this talk, we show an end-to-end approach to DOM breakdown monitoring and quantification of this break. The overall system is complex. It's complex to work with real life, with active system. When comparing various linear and CNN method, the CNN method outperformed the linear methods, and the proposed ER scheme is actually the one that both have allow us to bring some of the knowledge from the lab to the field, and resulted in with the best estimation of low concentration, which is essential for us. Thank you.
Thank you very much for this very interesting talk. As we are talking about optics, I would like to start with the question why you choose PMT. PMT, it's very expensive and not so robust. I saw in the slide you mentioned the bias of the PMT, and there is a lot of things. It's very sensitive if you are trying to compare between different systems. So why you choose PMT?
Well, I'm here. You hear me all right?
Okay. Yes, we can hear you very well.
We start with the PMT because at the time we didn't know what is the expected level of concentration, and so we believe that we need the most heavier equipment. Something with the best amplification. So the PMT provide us amplification in the order of 2 million for each electron for each photon, and this more or less was good guess, though we believe now we can use a SIMP or something which a silicon multipliers, which are one order below and much more cheaper. So, and also we are preparing, intend to work on the SNR issues, on the top of what we already have to lower the price or of the equipment. But if you have a PMT, you can always to check that you can lower the reverse bias and mimic lower SNR or a lower quality sensor.
Okay. As you are presenting intensity experiment, you are measuring spectra and you are measuring the intensity. The fluorescence intensity influenced for many parameters. For example, the distance of the detector from the sample, the orientation, the attenuation on your LED. You present 2 LED at light source. How are you eliminating all of these variations in order to have significant results in your fluorescence intensity experiments?
Well, we start with that, as I say, that first we didn't know. So at the time we were suffering from many problems like inner filtering, and we have to make sort of all kind of auxiliary testing to set, to make a proper design of the measuring chamber. That was one thing, and we always have some sort of measurement which is an integration results. We are measuring inflow and we're making some sort of averaging in time. So we have some averaging embedded, some averaging value, of what we measured. We compare ourselves to lab measurement, and on the top of this, I didn't get into that. I said it. I just said it in. As a point, we actually can learn the response of the system. We can measure upon having a data set. We can measure measure the same solvent in a stabilized fluorometer system in the lab, and then afterwards we know what to expect from the lab system, and we can actually learn the difference in responses. So we can reflect that, but we need to add to the our model the behavior of the system, and to this end we are not. We didn't done that yet, but we have the mathematical infrastructure in our in the suggested deep learning algorithm.
Is it commercial project or only research? What is the perspective of this?
To this end, it's a research project. It was funded by the chief scientist of agriculture, and I hope it could be, commercialized. But there are some steps needed. First one is lowering the price of the device.
Yes, no doubt. Personally, I would like now to encourage you. We have a lot of audience to come and visit me. I told you that we are working on water quality and measuring without fluorescence, and this is opportunity to invite you again and to establish a new collaboration in this area.
Yeah, sure.
Thank you very much, Iftach, and thank you all the audience that stay with us until now. I'm sure you enjoyed both high quality lectures and a lot of inspiration and new things that we can follow on. Stay safe, and hopefully next year face-to-face this event or other optic event in Israel. Goodbye.